Matter in nature can be broadly classified into solid, liquid, and gas based on their physical states. We will study the physical properties of those three phases in the next two chapters. Now, let's take a journey into the world of gas. If someone asks you what gas is like, how can you tell him about it? You may say it's something like air or water vapor. Or you may want to generalize it by describing the characteristics of gases. What are gases like? Gases tend to fill a container of any shape or size by expanding spontaneously. Because of this, the volume of a gas equals the volume of its container. They are highly compressible, as you may know from day-to-day experiences. Different kinds of gases can mix spontaneously and make homogeneous mixtures. One important thing to note is that gases of different kinds have similar physical properties, even if they have different chemical properties. In gas phase, the distance between molecules, or intermolecular distance, is so large in comparison to that in liquid or solid phase. Each gas molecule behaves as if the others are not present. This is due to the fact that under the normal circumstances, the gas molecules take up only about 0.1% of the total volume. That is why the molecules in gas phase have similar physical properties, no matter how different they are in chemical nature. The properties of gases can be described by pressure, volume, temperature, and number of moles. Pressure is the force applied to a unit area. This conceptual definition of pressure can be expressed mathematically as force divided by area, or F over A. Let me take some examples to illustrate the pressure area and pressure force relationships. Imagine that the equal vertical force is applied over different areas. Which one would produce greater pressure? The force applied to the smaller area or the force applied to the greater area? Since area is in the denominator, the smaller area will make the pressure greater. Let me take a couple of real-life examples. Imagine that a lady with tennis shoes on steps on your toes by mistake. Well, you may laugh it off and ask her nicely to move her foot away. But what if the same lady wears high heels? You surely will scream to death. No matter she wears tennis shoes or high heels, her body weight remains the same, or the vertical force remains constant. However, the contact areas in the two cases are different. The high heels provide smaller area of contact, and the vertical force is concentrated on that smaller area, producing greater pressure. Now, can you see how pressure and area are related? The smaller the area becomes, the greater pressure is produced. They are inversely proportional to each other. Now, let me show you how pressure and force are related. This picture shows a cylindrical container that is filled with water. It has 3 holes that are equally spaced and vertically aligned. It is certain that the cross-sectional areas at the locations of the 3 holes are equal. However, the weight of water or the vertical force exerted by water is least at the top but greatest at the bottom. the length of ejected water is proportional to the pressure. It implies the fact that the greatest vertical force is at the bottom and produces the greatest pressure. It further implies that pressure is directly proportional to the applied force as long as the cross-sectional area remains constant. Atmospheric pressure is the weight of air per unit area. An Italian physicist and mathematician, Torricelli, performed an interesting experiment to measure atmospheric pressure. He used a 1.2 meter long glass tube and filled it with mercury. He sealed its open end by placing his finger over the end and inverted the tube into a dish containing more mercury and removed his finger. He noticed that the mercury in the glass tube flowed down and stopped at a certain height. He realized that the height of the mercury column is dependent on air pressure. The air pressure exerted on the surface of mercury in the dish is equal to the pressure exerted by the mercury in the glass tube. If you bring the same mercury column from the sea level to the summit of Everest, what would happen to the height of the mercury column? Would it increase or decrease? Since the air at the summit of Everest is noticeably less than that at the sea level, the height of mercury column will decrease. Let's calculate the magnitude of pressure exerted by a column of air with cross-sectional area of 1 meter squared that is extended through the entire atmosphere. The mass of the air column is approximately 10,000 kilograms. We learned in high school physics that force is mass times acceleration. Since the force that we are dealing with is vertical force, the acceleration can be replaced by Earth's gravity, g, which is 9.8 meters per second squared. The force is 10,000 kilograms times 9.8 meters per second squared, which is equal to 1 times 10 to the 5th kilograms meters per second squared, or 1 times 10 to the 5th newtons. Since the pressure is defined by force over area, the pressure of the air column is 1 times 10 to the 5th newtons divided by 1 meter squared, which is equal to 1 times 10 to the 5th newtons per meter squared and 1 times 10 to the 5th Pascal. Standard atmosphere pressure is 1 atm, which is equal to 760 millimeter mercury or 760 torr, or 1.01325 times 10 to the 5th Pascal. As I said in the previous slide, the physical state of a gas can be described by 4 variables: pressure, volume, temperature, and number of moles. There are 3 gas laws that show the relationships among those 4 variables. The 3 gas laws are Boyle's law, Charles' law, and Avogadro's law. The Boyle's law demonstrates how pressure is related to volume at constant temperature and quantity. Look at this illustration. Let's assume that the cylindrical container has fixed amount of gas. The movable piston keeps the gas inside the container, so the quantity of gas or the moles of gas remains constant. Assume that the temperature of the gas also remains constant. When you push the piston to compress the gas inside, what would happen to the volume and pressure of the gas? As the gas is compressed, the volume of the gas decreases and its pressure increases as a result. It implies that the pressure and volume of gas are inversely proportional to each other. This leads to Boyle's law. It states the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. This can be expressed mathematically like this. You may use a proportionality constant K, and the expression can be written V equals K times 1 over P, or simply PV equals K. It implies the pressure of gas multiplied by its volume always makes a fixed value, no matter what state the gas is in, as long as the temperature remains constant. Experimental evidence of Boyle's law is given in these two graphs, demonstrating the volume of gas is inversely proportional to pressure and directly proportional to 1 over pressure. The Charles law shows how temperature is related to volume at constant pressure and quantity. Look at the picture on the right. An air-filled balloon is immersed in liquid nitrogen. The temperature of liquid nitrogen is below -196 Celsius or -321 Fahrenheit. Under such low temperature, the air inside a balloon is cooled and liquefied. This leads to a sudden decrease of the volume of the balloon. When it is taken out of the liquid nitrogen, the temperature of the balloon increases gradually, and its volume also increases gradually. Once the temperature of the balloon increases to room temperature, it recovers its original shape. This demonstrates that the volume of gas is directly proportional to temperature. This leads to Charles' law, stating the volume of fixed amount of gas at constant pressure is directly proportional to its absolute temperature. This can be expressed mathematically, V equals K times T, or V over T equals K. Take a note that the lowercase k represents a proportionality constant. Experimental evidence of Charles' law is shown in this graph. The volume of gas is plotted with respect to temperature in Celsius. It clearly demonstrates the trend of increasing volume of gas as its temperature increases. Take a note that the red best fit line is extended and crosses x-axis, or axis of temperature, at -273.15 Celsius. This is called absolute zero, or 0 Kelvin. So 0 Kelvin is equal to -273.15 Celsius. Be aware that the temperature in Charles' law is in absolute temperature scale. Avogadro's law shows how volume and moles of gas are related. It states the volume of gas at constant temperature and pressure is directly proportional to the number of moles of the gas. This can be expressed mathematically, V equals constant times number of moles N. Interestingly, the volume of 1 mole of any real gases are 22.4 liters at 0 Celsius and 1 atm. The volume of 3 real gases, helium, nitrogen, and methane, are shown on the right under the condition of 0 Celsius and 1 atm. I will talk more about it in the next slide. Boyle's law, Charles' law, and Avogadro's law shows that volume of gas is inversely proportional to pressure, directly proportional to temperature, and directly proportional to number of moles. These three gas laws can be combined into a single proportional relationship. That is, the volume of gas is proportional to NT over P. If we use a proportionality constant R, it turns into an equation. V equals R times NT over P. The proportionality constant R is called gas constant. This equation is called ideal gas equation, and it can be rewritten as PV equals nRT. Ideal gas is a hypothetical gas consisting of identical particles of negligible size with no intermolecular forces. It obeys the ideal gas equation. This 3D plot exhibits possible states that ideal gas may take, which is represented by the area in light blue. The gas constant R is 0.08206 liter atm per mole per Kelvin, or 8.314 joule per mole per Kelvin. Be aware that the two values have different units, but they are equivalent to each other. You are going to use the gas constant numerous times for problem solving. It is very critical to use the gas constant with an appropriate unit to get the correct answer. The volume of 1.000 mole of an ideal gas at STP can be calculated using the ideal gas equation. STP stands for standard temperature and pressure, which are 273.15 Kelvin and 1 atm. The ideal gas equation can be rewritten with respect to volume, that is, V equals nRT over P. Plug all the given values. Then it will be 1.000 mole times 0.08206 liter atm per mole per Kelvin times 273.15 Kelvin divided by 1.000 atm. The units of mole, Kelvin, and atm are cancelled. The remaining unit is liter, which is a unit of volume. Finally, the volume of ideal gas at STP is 22.41 liters. Be aware that you must use the appropriate gas constant in this particular problem, which is 0.08206 liter atm per mole per Kelvin, not 8.314 joule per mole per Kelvin, because the pressure of gas is given with the unit of atm. Interestingly, the volume of 1 mole of ideal gases at STP condition are almost same. This is one of the characteristics of gases that I mentioned at the beginning of the chapter. Now, let's try an online activity to reinforce our understanding of gas laws. Log in to the course site on the 2L. Click the Content tab at the top. In the left menu, open Lecture Material, then select the module titled 10 Gas Laws. Under that module, find Lab 10 Gas Laws and download a lab worksheet. Complete it as you work through the online simulation. Return to the 2L and, under the same module, open Simulation, Gas Laws. In a simulation, select the Intro window. Make sure to select the purple ball at the bottom. Check Width in the right menu. Select K for the temperature unit and ATM for the pressure unit at the top right corner of the container. Left-click the handle on the left of the rectangular gas container and drag it to adjust the width of the container to 10.0 nanometers. Pump the gas particles into the container by left-clicking and dragging the pump handle up and down. Observe how the pressure of the gas changes as more gas particles enter the container. Record your observations. Partially open the door of the container at the top by holding and dragging the door handle to the left. Let the gas particles escape through the opening. Record your observations on how the pressure changes as gas particles escape the container. Close the door and pump the gas until the pressure reaches 5.0 atm. If you pump too many gas particles, causing a higher pressure, partially open the door of the container to release the gas until the pressure gauge reads 5.0 atm. Make sure to close the door. Left-click the handle on the left of the container and drag it to the left until the container is fully extended. Hold the handle on the left of the container and drag it to the right until the container is compressed back to a width of 10.0 nanometers. Find a button on the heater cooler at the bottom of the gas container. Press and drag it up to heat the gas until the temperature of gas reaches 800 Kelvin. Press and drag the button of the heater cooler down to cool the gas until the temperature of gas reaches 500 Kelvin. Click the loss icon at the bottom. Make sure to select a purple ball at the bottom. Check width in the right menu. Select K for the temperature unit and ATM for the pressure unit at the top of the gas container. Pump the gas particles into the container by left-clicking and dragging the pump handle up and down until the pressure of the gas reaches 5.0 atm. Select Temperature in the menu titled Hold Constant. This would keep the temperature of the gas constant. Expand and compress the gas by dragging the handle on the left of the container to the right and left. Observe carefully how the gas pressure changes as the volume of the gas increases and decreases. Open the downloaded lab worksheet. Follow the step-by-step instructions and complete the lab worksheet.